AP Chemistry. This is the third and final lesson in the Intermolecular Forces unit, Unit 6. It's going to deal with heating curves and some other factors. You want to be sure you understand this. This is a heavily tested concept on the AP exam. So we're going to start with heating curves. Heating curves show the temperature increase or decrease associated with heat added or subtracted for a substance. The curve below is the heating curve for water at 1 atmosphere, which is the air pressure where you live right here. So let's take a look at it. Let's break it down here. So if you look at the horizontal axis, that shows you heat added. It's how much heat in joules that you're adding to the water. If you look at that's the horizontal axis, the vertical axis is the temperature in centigrade. So you see that it ranges from negative 30 degrees centigrade up to 140 degrees centigrade. So let's look at this down, starting at the bottom left and working our way up. So what you see, that sloped line that goes from negative 30 degrees up to 0, the water is in the form of ice. And so you see that's an increase of temperature of ice up to 0 degrees. Once it reaches 0 degrees, the ice starts to melt as it pushes above 0 degrees. But an interesting fact is, while the ice is melting, the temperature stays at 0 degrees. So while it's being converted from ice into liquid water, it stays at 0 degrees. And that explains the flat line there where you see in light blue it says melting. In the yellow box it says changing from solid to liquid. That would be from ice, solid state, to liquid water. Now we see the middle sloped line. That's the longer sloped line. And that's when the water is being heated. It's going from 0 to 100 degrees. So that's an increase in temperature. It doesn't boil at that point. It's just getting hotter and hotter. So it goes all the way up to 100 degrees. And that's when it starts to boil at 100 degrees. While the water is boiling away, it stays at 100 degrees. Because once a water molecule has an energy greater than the temperature equivalent to 100 degrees, it's going to vaporize. It's going to break away from the liquid water and float away. So that flat line, the higher of the two flat lines, is a changing state from liquid to vapor. You could call it steam if it's boiling, but it's vapor. In general, it's vapor. And that happens at 100 degrees. Finally, the sloped line up at the top is once all of the water has turned into steam or vapor, it can continue to increase its temperature at that point. And so it can increase above 100 degrees, and there it's doing that as steam or water vapor. So let's take a look at an example. Or let's continue to look at this. When you're doing this computation at points A, C, and E, where you see sloped lines, to compute the heat required to increase the temperature of a single state of matter. So down there at A, that would be ice, C would be liquid water, and E would be steam. We use the specific heat equation, the one that we use for calorimetry. So it's Q, the heat, equals the mass of the substance, times the specific heat of the substance, times the change in temperature. So each phase has its own specific heat value, C. So you'll see that in a moment. Now, to compute the heat for the flat areas, so the one down there at the bottom that's being pointed to would be where the ice is melting into liquid water, and we said that stays at 0 degrees as long as it's doing that. So there's no temperature change. So when you think about it, if there's no temperature change, you can't use the formula Q equals MC delta T because there is no delta T. So we have to use a different formula that doesn't include temperature change because there is none. So at point B, to compute the heat energy required for the phase change from ice to liquid water, we use the heat of fusion equation. Heat of fusion is the heat that has to be taken out of a liquid substance to make it fuse, that is, to get stuck together, that's what fusing means, into solid. That in the case of water, that would be ice. Now, if you go in the other direction, you put heat in to turn it from ice into liquid water. However, it's still called heat of fusion. You're not fusing the molecules, you're breaking them apart. You're doing the opposite. But it's still called heat of fusion because it's the same number. It's just a matter of you put the heat in if you want to melt ice into liquid water. You pull the heat out the exact same amount if you want to turn liquid water into ice. You want to freeze it. So it's called the heat of fusion in either direction. Okay, so here's the formula. The heat is Q equals the number of moles times the heat of fusion. And every substance has its own heat of fusion, just like it has its own specific heat. And for water, the heat of fusion for water is 6.07 kilojoules per mole. Again, that's only for water, but that's what we're interested in this example. Now, the higher flat line, the one that's taking place when the water is boiling into steam, so there the temperature stays at 100 degrees. So again, we don't have any temperature change. So at point D, to compute the heat energy required for a phase change from liquid water to water vapor, we use the heat of vaporization. And you see the equation looks exactly the same as heat of fusion, except you use a different delta H number. It's called the heat of vaporization. Again, that's a fixed number that you can look up for a substance. So the heat of vaporization for water is going to be 40.67 kilojoules per mole. All right, and that's called the heat of vaporization. Again, vaporizing is when the liquid water becomes vapor, it turns into steam. But it's still called heat of vaporization, even if you're going in the other direction. If you're condensing steam back down into liquid water, that's called condensation. It's still called heat of vaporization. It's the same number, it's just whether you're putting heat in or taking heat out. Okay, so here we go with an example. We are going to go from negative 25 degrees to 125 degrees, and we're going to start with ice at negative 25 degrees. We're going to heat it up. We're going to melt it, turn it into liquid water, heat the liquid water from 0 to 100. Then all of a sudden it starts to boil, and you boil it all the way at 100 degrees, and then you increase putting heat in so that vapor, that water vapor or steam, increases up to 125 degrees centigrade. Okay, so that's our objective. What we want to figure out is how much total energy does it take in kilojoules to get from the negative 25 centigrade to 125 degrees centigrade. So step one, we're at point A. We're heating the ice from negative 25 to 0. It stays at ice as long as it's between those two temperatures. Now the C for ice is not the same as it was for water. If you remember back to calorimetry, for liquid water it was 4.18 joules per gram Kelvin. For ice it's a different number. Again, it's a fixed number that you could look up in a book or look up on Google. This is the heat that would be required. This would be the specific heat for ice. So there's the formula down there in the bottom left. It's the same one we use for calorimetry. So now it's asking you about 1 mole of water. So notice that the formula Q equals mc delta T, m is mass. It has to be in grams. So the first thing we have to do in this formula is turn 1 mole into a number of grams of water, because the formula says we have to have mass in grams. So there you see a molar mass. The first two steps, the first two numbers are 1 mole times 18.02 grams per mole. That's just a molar mass conversion to convert 1 mole of water into a certain number of grams of water. Okay, and that would be 18.02 grams of water. So now we have a mass for the water. Okay, and then we use the specific heat for ice, which is 2.03, and the temperature change is positive 25. So that means that 0.91 kilojoules of heat will be added in getting the ice from negative 25 up to 0. You still haven't melted any of the ice at this point. It's still completely ice. But you're just getting it from well below its freezing point up to its freezing point, which is 0 degrees. So 0.91 kilojoules of energy is required to do that. Okay, now we're ready to move on to the next step. Step 2, and this is where the ice melts into liquid water, and it does that at 0 degrees. That's the freezing point of water, or it's the melting point of water, whatever you want to think of it as. And it stays at 0 degrees as long as the ice is melting. So for that, we use the heat of fusion. Now the units of measure for heat of fusion, well, you see the number there at 6.01. That's a fixed number for water. You can look that up in a table in a book somewhere. It's kilojoules per mole. So you see the formula down at the lower left. It's Q, heat, equals moles, number of moles, times the heat of fusion. So notice you don't have to do the molar mass conversion that we did on the last step, where you had to convert to grams, because the other formula requires mass. This one requires moles, so just pay attention to that detail. So we have 1 mole, that's what we said we're starting with. The heat of fusion is expressed in kilojoules per mole, 6.01, and so you multiply that, you get 6.1 kilojoules. So we're going to go ahead, we're keeping a running tally of the energy that we have to put in. So there you see in the upper right corner, you have the 0.91 from the first step, step A, and the 6.01 from the second step, this step right here. So we're going to just keep adding the heats as we go through this, through these phase changes. Okay, third step is C, point C. So now you're heating the ice from 273 Kelvin to 373 Kelvin. That's the same as 0 to 100 centigrade. And there you see the familiar number there on the right that we used in calorimetry. The specific heat of water is 4.18 joules per gram Kelvin. So down in the lower left, you see the equation that we used to relate the change in temperature to heat. And again, we have 1 mole, but we have to convert it into grams because the formula calls for mass, and mass is measured in grams. So we have to do the first 2 numbers you see there are molar mass conversion into grams, which is simply 18.02 grams of water. There's the specific heat, just like we did before, and there's the temperature change. And again, it doesn't matter whether you use Kelvin or centigrade if it's a temperature change, because 100 degrees on the Kelvin scale and 100 degrees on the centigrade scale are exactly the same. I would say, however, if in doubt, convert to Kelvin. That is the absolute temperature scale, and I would convert to Kelvin if you're not sure. Okay, so we do the math on all that, and we get 7.52 kilojoules of energy is required to take water just past its melting point, where it's totally melted into liquid water, all the way up to its boiling point, but before it starts to actually boil. You would require 7.52 kilojoules. So that's the sloped line C. Now you see in the upper right again, we're keeping a running tally of how much heat energy we're putting in. So first step, second step, and now we're at the third step. And now we'll go on to the fourth step. Okay, now we move on to step 4, and that's at point D. That's the flat line, and that's where we're boiling water. So we're going through a phase change from liquid water to steam or vapor. The temperature stays at 100 degrees centigrade, or that would be 273 Kelvin, at constant temperature. And there you see the heat of vaporization. The delta H vaporization is 40.07 kilojoules per mole. So again, we're going to go back to the equation Q equals number of moles times heat of vaporization. You don't have a temperature change, so you can't use the other formula for this. That's just the way to remember it. If there's no temperature change, you can't use a formula with delta T in it. So we have 1 mole. We have the heat of vaporization, which is 40.67 kilojoules per mole. So that gives us 40.67 kilojoules. And we're going to add that to our list in the upper right corner. We have to add that much heat to convert all of the water from liquid into vapor form. Finally, we're going to do the fifth. Okay, and so now we're moving on to step 5. Now at the sloped line E, we have all steam. Everything is in the form of water vapor or steam. So what you're doing at that point is you're raising the temperature of steam above the boiling point of water, which is 373. That's something you'd want to do if you're running a steam engine and you want very high water pressure. You want as much energy in those vapor molecules as you can get, so you can push a big old-fashioned steam train, for example. So the specific heat of vapor, of water vapor, again, it's a number you can look up on a table, it's a fixed number, is 1.84 joules per gram Kelvin. So we go back to our heating equation that includes delta T. So we said we were going from 100 degrees up to 125. So first you do the molar mass conversion to get the mass of 1 mole of water. Then you multiply by the heat, the specific heat of vapor, and then by the temperature change, which is 25 degrees from 0 to 125, and you get 8.30 kilojoules. And so now we can add that to our list, and we're done with our calculations, and we compute that the delta H is positive 56.0 kilojoules. That's the heat that was put into the water to go from negative 25 degrees centigrade all the way up to 125 degrees centigrade. So become familiar with this calculation. They wouldn't ask you to do this entire calculation on the AP, but definitely they could ask you to do one part of it, okay? So you should understand how to do this. So the total enthalpy change required to heat 1 mole of water from negative 25 degrees centigrade to 125 degrees centigrade is delta H equals positive 56 kilojoules. Now we're going to look at some unrelated topics, but just some things to close out this unit. One thing the AP does not spend much time on, but there's a few things you should know, has to do with solids and the structure of solids. So there you see on the left a crystalline solid. The crystalline solids form organized structures with flat surfaces. Examples would be diamond and quartz. Amorphous solids have irregular arrangements of atoms. Examples would be glass and rubber. And so the molecules are just a little bit helter-skelter put together like that, as you can see. It may not surprise you that rubber is like that because you know rubber bends. It might surprise you that glass has that structure because you kind of think of glass as having, you know, nice, pretty, clear, and you would think that it would be very orderly structure, but it's not. Glass is actually amorphous like that and has irregular shapes to it. Crystalline solids can take on 14 different types of structures called Bravais lattices. There they are. I'm just showing them to you. You don't have to know them all, but you should be familiar with 3 of them. The top 3 are the most basic ones, and you should be familiar with those. So you only need to know the first 3, which are simple primitive cubic, face-centered cubic, and body-centered cubic. Okay, so let's define. A coordination number is the number of atoms surrounding any atom in a lattice structure. Percent occupied is the percent of a unit cell that is occupied by atoms. The rest is empty space. So there are actually, if you're interested in geometry, there's some really kind of fun geometry problems you can do to figure out distances, atomic radii. Remember, we did talk about atomic radius, basically the radius of an atom, and it didn't seem to have much importance up until now, but it is important in understanding the structures that solids take on, because it has to do with how big the atom is and how many of them you can fit into a certain amount of space. Again, we're not going to go deep into this. It's a very, very just kind of a superficial treatment of this, but let's just talk a little about it. So a simple cubic structure, lattice structures have atoms at the corners of a cube, like you see in figure B right there. Coordination number. The coordination number is 6. What is coordination number? Down at the bottom it says the number of atoms surrounding any atom in a lattice structure. So there are 6 atoms surrounding any atom in the lattice structure. Now what I'm about to say might not be obvious, and don't worry about it too much if it's not totally clear, but let's just try to figure out how many atoms would be surrounding any one atom. So let's take that partial atom. You see that looks like a slice of an atom there. Again, these are slices, and specifically each one is 1/8 of an atom. If you figure it out, you got an 1/8. If you put another 1/8 around that one and another, and then you do the same on top, you'll have a round atom. You'll have a sphere. So you're seeing 1/8 of a sphere, which you're looking at there. So let's take the one in the upper right corner. You can see that it has an atom down below it, an atom to the right of it, an atom to the left of it. The one behind it, the one furthest in toward the Hoover High Cardinals, that one is not touching it, so that doesn't. See that there are 3 atoms touching it right now. The 2 up above on the left and right, and the one down below. Now if you imagine you extended that unit cell out, there would be another atom on top, there would be another atom to the right, and another atom to the left. That would be a total of 6. If that's not totally clear to you, kind of use your imagination, see if you can see what I'm saying. There would be a total of 6 atoms touching that atom in the one that's closest to you on the top. Now, there's using the geometry that I talked about, you can figure out that 52% of that cube is occupied by atoms. So the blue is 52%, and the white is the remaining 48%. Okay, so that's a simple cubic. Okay, there in the center you see a body-centered cubic, and you can see why it's called that. It has one complete sphere, one complete atom in the center of the unit cell. So you can see it's being touched on 8 different sides by 8 different atoms. You can see 3 down on the bottom, and the 4th one is back behind it that you can't see, but it's there. And then you see the 4 on the top. So that one's a little easier to visualize, that there's 8 different atoms that will be touching that. And that, again, is called the coordination number. How many atoms are touching any one atom? And in a body-centered cubic, 68% of the cube is occupied. That means that cube, 68% of it is blue, and the other 32% is the white, is the space that's not being occupied. Finally, we go to the face-centered cubic unit. And unit cell, they have a half atom on each face and 1/8 of an atom on the corners. Again, this one's a little hard to visualize, but the coordination number is 12. So if you take that atom that's right out in front that's facing towards you, it has 4 atoms behind it. You can see 2 of them, the one that's facing up and the one that's facing to the right. There's also one that's facing to the left and one that's facing down. So that's 4 behind it. Then you can see those sections that are right up close to you there, those 1/8 sections. There's 4 of those. So that you add another 4 atoms, and that's 8. And then what's not shown at all, but you kind of have to use your imagination, is out in front of the computer screen, there's going to be 4 more atoms. They look like the ones that are in the back there that are touching it. They're going to be in the front touching it. So there's going to be, if you look at that, that face that's facing straight out towards you, that's going to have 12 different atoms touching it. So its coordination number is 12, and 74% of that cube is occupied, which means that 26% is empty space, is the white area. All right, so again, just become kind of familiar with these, and they might ask you a question on this on the AP. It's not a heavily tested subject, but be aware of it. So let's talk about some different types of solids. Molecular solids are substances held together by intermolecular forces, dispersion forces, dipole-dipole, and hydrogen bonds in solid form. Ice, frozen water, is the most common example of a molecular solid. Argon and carbon dioxide can also form molecular solids at very low temperatures. And for argon, it would be a very, very low temperature. So there you see a water molecule, just a lone water molecule. Down below, you see it in a hexagonal structure that ice forms because of the hydrogen bonds. And then you see it layered over there on the right. Okay, so it can form layers like that. Covalent network solids are formed by a large series of covalent bonds, and they're somewhat similar to lattice structures, except they're covalent bonds, not ionic bonds, that form them. Diamonds are pure carbon atoms bonded in a 3-dimensional tetrahedral structure. And we'll learn about the different geometry structures in a couple of weeks, but that's an example of the structure of diamond. It's the hardest substance on Earth, and it forms that 3-dimensional structure. Now, graphite is a soft 2-dimensional layered structure. Again, it's pure carbon. Both of those molecules, structures, are pure carbon. So diamonds are pure carbon atoms bonded in a 3-dimensional tetrahedral structure. Graphite is a trigonal planar. Again, we haven't gotten to that term yet, but we will shortly. Is a trigonal planar arrangement of carbon atoms in layers that can slide across each other. So graphite is soft, and it's used in pencils. So when you write with your pencil, what you're doing is taking one of those layers that you see over there on the right, and you're laying it down on the paper. And then you make another mark, you're laying down another layer. So it's very soft, and those layers can come off very easily, and that's what your pencil uses to make marks on the paper. Okay, so we're going to talk about a concept we talked about earlier, but it's an important concept to understand. Why does water have a backward sloping phase diagram? In other words, where you see the line between the blue where it says water and the white where it says ice, why does that lean to the left? Okay, so at high pressure, B, so notice B is above A on the pressure on the vertical axis. At high pressure B, water molecules are crushed together and are attached to each other mostly by dipole-dipole bonds. Okay, so what we said is that in ice form, let's go ahead and read it. At lower pressures A, the water molecules are not crushed together. They're not being pushed together. They're at lower pressure. And they can stretch out and form hydrogen bonds that allow water to form hexagonal crystal structures. So you see the liquid water down below. It looks kind of chaotic. They're kind of just all jumbled around each other, but you can see that they're much closer together than on the right, where you have that pretty hexagonal structure, and that's ice. Again, it's hydrogen bonds are forming the ice. And so they attach a hydrogen from one water molecule. They connects with the lone pair of a different water molecule, and that forms that pretty structure based on the shape of a water molecule, which is kind of a bent angle molecule. So that happens at low pressures. Generally substances, let's review this, generally substances at lower pressures can spread out a little more. The molecules can spread out, and so they're looser, and so they can move around each other and be a liquid. But when they're squeezed together at high pressure, they can't move around each other very much. They're being pushed together so tightly, and so that forms a solid. So for almost any other substance, at low pressure you have liquid, and at high pressure you have solid. Water is the opposite. At low pressure, you have the solid because those molecules can stretch out and create hydrogen bonds. They're not being pushed together. But as you go to higher pressure, you kind of crush that hexagonal structure, those hydrogen bonds, and it becomes the jumble that you see down there where it says liquid water. So the key, this explains why water has a backward negative sloping fusion curve, very unusual and very likely a question on the AP exam. Viscosity. So viscosity is the resistance of a liquid to flow. You don't really need to do any calculations with viscosity unless I learn otherwise. It's just something to know what the term means. So pancake syrup is more viscous than water. It flows more slowly. Surface tension exists in liquid molecules because the molecules on the surface of water are, and it's not just water, but water is the common example, are pulled only inward toward the interior of the water and toward other surface molecules. Molecules in the interior of the water are pulled in all directions and therefore do not exhibit this tension. So you can see that illustrated below. A water molecule inside the liquid is pulled in all directions by polar bonds, by dipole-dipole interactions with other water molecules, so it doesn't feel tension in any one direction. But a water molecule on top is only pulled downward by other water molecules. Air molecules don't pull up on the water molecule. Air molecules are nonpolar. That would be nitrogen N2 and oxygen O2. They will not pull up on the water molecule, so it's only being pulled down and to the sides, and therefore it forms what seems like a little plastic layer on top. And so things can float on it. And you see that water bug over there. It's standing on water, and you can see how it makes little indentations there. And we're going to do a little project with a paper clip to demonstrate that. Okay, that takes care of this lesson, and that takes care of the unit on intermolecular forces. We'll go through a lot of questions in AP Classroom and in the Princeton review book on this because it's really a conceptual subject, asking you to do an entire heating curve is not something they would ask, although, as I said, they would ask you to do maybe a part of one or answer just a question about one. But you want to understand these concepts and this relationship of intermolecular forces. Again, chemical bonds create new substances. Metallic, covalent, ionic bonds attach atoms to each other to create new substances. Intermolecular forces simply take molecular, covalently bonded molecules and determines whether they stick together or not. Low energy from the outside, they stick together strongly and become a solid. Medium energy from the outside, heat energy from the outside, they kind of stick together, so they form a liquid. They stick together, but they can move around each other. And high energy from the outside will overcome the intermolecular forces, and it will cause them to become a vapor or a gas. And that takes care of this lesson, so we'll see you next lesson.